In this video, I'm going to explain you about the external direct sum. Okay, so we are taking vector spaces, different vector spaces over the field F. So here I'm taking V1, V2, V3, so on till Vn are vector spaces over the field F. Okay, then I'll consider one set which consists of n tuples. Okay, which consists of n tuples, and each of them, each v1 v2 like this, each of them should belongs to vi. Means if I take v1, v1 will belongs to the vector space v1, v2 will belongs to the vector space v2, and so on. Okay, so this, let I take two elements from v, so I'm taking v bar and w bar belongs to v. So v bar is of n tuples of this type, and same way w bar will be also n tuples of this type. Okay, then we are defining the addition in this v. So v bar plus w, how we add? We add coordinate wise. Okay, so v1 plus w1 comma v2 plus w2 and so on, vn plus wn. Okay, and we are defining the scalar multiplication here to be alpha n tuples. So you multiply each coordinate with alpha. Okay, where alpha belong to the field. Then we have to show that this vector, this v, is a vector space over the field F, and this v is called nothing but the external direct sum of v1 v2 till vn, given by v is equal to v1 plus e, means e donate the external sum v2 plus e plus so on, plus here also we have plus e vn. Okay, and this external sum, see this v is equal to, so we have written here v, we can write here v equal to, we wrote here v1 external sum e, v2 external sum e, plus so on, plus external sum vn, which is similar to the cross product of each vector space. Okay, which is similar to the cross product of each vector space, that is v1 cross v2 cross v3 cross so on till vn. Okay, so this external direct sum is same as the cross product of the vector space. Okay, or the product of vector space, or we can say the cross product of vector spaces. Now we have to show that this v itself is a vector space over the same field F. Okay, so we are going to show that this v is a vector space over the same field F. So first of all, we try to show that v is an abelian group under addition. Okay, so I can check easily that v is non-empty. Why it is non-empty? Because this element will belongs to v, where this 0, okay, this 0 is the 0 vector, okay, is the 0 vector in v1 vector space. Okay, and this 0 is the 0 vector in v2 vector space, and so on like this. So this 0 represent that, where 0 belongs to vi for each I, means each I means these are the 0 vectors in each vector spaces. Okay, next we try to show that it is associative. So we are trying to show this is associative here. So we get v bar plus w bar. It is clearly binary, we know, because we get again the same element, so it is binary. Okay, number two, I'm showing the associative property here. Okay, so it is associative. So v bar plus w bar plus z bar, okay, which is equal to, we add in this way, so we'll add coordinate wise. So we get v1 plus vw1, v2 plus w2, vn plus wn, and we add with this. Again, we add coordinate wise, so we get to be this. Okay, we are getting this. Now here, see here, these are vector space, elements of the vector space. Okay, these are elements of the vector space. So as associative law holds in the vector space is, okay, so we can interchange this. Okay, because the associative law hold in the vector space, so that's why we can interchange this. Okay, so we get this in the same way we'll get here also. Now this can be broken as v1 v2 till vn plus w1 z1 w1 plus z1 so on till wn plus zn. So this also can be broken, so we get this, so we get v bar plus w open bracket w bar plus z bar. So that shows that the plus is associative in V. Okay, plus is associative, and we can see that this is the additive identity element of V. Okay, this is the additive identity element of V. So if I take any vector in V, then it will be of n-tuples. So the inverse, suppose I take this is the vector in V. So the additive inverse of this is nothing but the minus V1 minus V2 dot 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 minus Vn, which belongs to V. Okay, and this is the inverse of this. Okay, so every element has an inverse. Next, we are trying to show abelian. Okay, so we are trying to show the abelian. So we have this V1, V2 dot 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 till Vn. We add these two, so we add coordinate wise. Okay, so since these are elements of the vector space. Okay, these are elements of the vector space of the same vector space. These are elements of the vector space V1. Okay, V1 and W1 both are elements of the vector space V1. So V1 is an abelian group under addition, so we can interchange this. So we get W1 plus V1. Same way here also, V2 is the vector space, so it is an abelian group under addition, so we can interchange. Same way for all these coordinates, we can interchange. Then we can break this into two coordinates. We get W1 till Wn, V1 till Vn. So we get here we have taken V1, V2 plus dot 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 till Vn plus W1, W2 dot 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 Wn. We have shown that is equal to W1 dot 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 Wn plus V1, V2 dot 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 Vn. So we have shown that this plus is an abelian, means every element is commutative under addition. So this V is an abelian group. So we have shown that V plus is an abelian group. Now we'll try to prove the fourth condition of the vector space. Okay, we'll try to prove the fourth condition of the vector space. So I take a vector V to be this and W to be this, and I take two scalars. Then the first condition of the vector space. So we add two vectors. So we are adding here two vectors. So I'm taking this, we'll add coordinate wise. So using the second definition of scalar multiplication, I have to multiply each scalars to each coordinate. So I multiply like this. Okay, I multiply this, then I'll multiply alpha 1 here also I'll multiply with alpha W1, and so on this way. So I can separate this into two coordinates. So I separate this one into two coordinates, I get this. I can take alpha common from here. In the same way, I can take alpha common from here, so we get this. Okay, so that is alpha V bar plus alpha W bar. Next, the condition, condition here we have alpha plus beta V bar. So you multiply this to each coordinate, so we get this. Then V1 you multiply inside, so we have this. So this can be separated into two coordinates, so we have separated here. From here you can take alpha common, here you can take beta common, so we get this. So the second condition is also proved. Now the third condition, alpha beta V bar, this can be written as alpha beta V1, V2 till Vn. So you multiply to each coordinates. Now since these are elements in the vector space V1, it will follow the property of the vector space, so it can interchange. So this is following the property of vector space and interchanging, so we get this. Now alpha is also scalar, it will come out, so we get beta V1 comma beta V2 and so on till beta Vn. So beta, so you can take out, so we get beta common, so V1, V2 till Vn. Okay, so that is alpha beta V bar. So the third condition is of the vector space is also true. 1 into V bar. Now you multiply 1 to each. Now this one is a vector element of the vector space. So 1 into V1 is V1, we know. And this is an element in V2, vector space V2. So 1 into V2 is also V2. Okay, so in the same way, 1 into Vn will be Vn. So we get here V1, V2 till Vn, which is equal to V bar. So it holds all the condition of the vector space. Hence, V is a vector space over the field F. And it is denoted by this, which is the external direct sum of the given vector spaces. Thank you.